In this video, I'd like to talk about the math question of the day for Saturday, August 12th, 2023. And with this problem, we need to use the definition of the derivative to find the derivative of this function w of z. And derivatives are typically taught in a Calculus 1 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And we need to use the definition of the derivative to find the derivative of this function. So let's quickly remind ourselves what that definition is. We can do a quick derivation. We can make a coordinate plane here, and let's say we have some function. We can call it whatever we want. Let's call it f of x. And remember, the derivative is essentially looking at how steep the curve is at any given point. Or in other words, it's looking at the rate of change of the function. How does the function change as x gets bigger? And the way to approach this is to first start by using techniques from algebra. We start by looking at 2 points. We can say this is x sub 0, and we look at a point that's close to this. We can call this x sub 0 plus h, and what we can do is draw a line between these. We can draw a secant line, and this secant line will tell us the average rate of change of the function if we find the slope of this secant line. Now, this will give us a rough approximation for how the function changes, but in calculus, we want to know exactly how it's changing, not just an approximation. So what we do is let this h value get smaller and smaller. Essentially, we have this point move along the curve and start getting closer and closer to our point in question. And in some sense, it will end up right on top of our point, so that we really only need 1 point to find the derivative, or the rate of change of the function. And once we find that 1 point, it will no longer be a secant line. We will now be looking at what's known as a tangent line. It will just touch the curve at this 1 point, and the slope of that tangent line will tell us exactly how the function is changing at that point. And in essence, we're going to take a limit. We'll take the limit as h approaches 0. We're going to make this h value smaller and smaller so that these points approach each other. And we're looking at the slope of this line here, the slope of the secant line. And remember, that slope can be defined as the change in the function value divided by the change in the independent variable. And the change in the function value, we have f of x0, x sub 0 plus h, minus f of x0, all divided by x0, x sub 0 plus h, minus x sub 0. This is the slope of this secant line, though, like I said, we're going to take a limit as h approaches 0. And this right here, if we simplify it, is the definition of the derivative. So let me quickly rewrite this, though in the denominator, x sub 0 minus x sub 0, those will cancel out and we'll just have h. So I will rewrite this with the denominator simplified. Now, I should mention there are other ways to define the derivative, though they are equivalent to this. And if you want, you can use just x rather than x sub 0. But let's actually apply this definition to our function, w of z. We are finding the derivative of our function w with respect to z here. We have w prime of z. And basically what we'll do is we'll plug in z plus h. We're just replacing x sub 0 now with z in our definition. We'll replace anywhere we see z squared for this first part in our numerator with z plus h. So let's do that. We will have 4 multiplied by z plus h squared minus 9 times by z plus h. That is this first part, and then we'll subtract off the function evaluated at z, which would just be this function, 4z squared minus 9z. And I also recognize I forgot to put the limit part in here. That is important. In the derivative, we do let h approach 0. So let me rewrite this with the limit notation. And now that we've applied our definition of the derivative, we just need to simplify this quotient here and then take the limit as h approaches 0. And basically, we just need to expand this term here. So we have the limit as h approaches 0, and we'll multiply out this quadratic. It is a perfect square. We will have 4 multiplied by z squared plus 2zh plus h squared. And then we'll distribute this negative 9. We have minus 9z minus 9h. And we still have this part. We have minus 4z squared and plus 9z. And then all of that will be divided by h. And right away we can notice that this minus 9z plus 9z, that will cancel. And we can simplify further by distributing this 4. We would have 4z squared plus 8zh plus 4h squared. And we have minus 9h minus 4z squared. And all of this is still divided by h, but notice that we have 4z squared minus 4z squared. So those will cancel out. And notice now that each of these remaining terms has h in it. So we can divide all of these by h to simplify this expression. We still have the limit as h approaches 0, that we now have 8z plus 4h minus 9. And we divided everything by h, so we no longer have our denominator. And lastly, we can actually take the limit as h goes to 0. Essentially, this term here will approach 0. So the derivative would be 8z minus 9. And we found that derivative using the definition. Though, if you know the power rule, you can check your work. Remember the power rule, we just bring down the exponent, we multiply, and then subtract the exponent by 1, which means we have 8z to the first. And with this minus 9z, this is to the first power. We bring the 1 down, we multiply, we get minus 9, and then subtract the exponent by 1, so we have z to the 0. But anything to the 0 power is 1, so we can just leave this as minus 9, meaning that 8z minus 9 is definitely the correct answer.